Right, we should make a start. So, first of all, welcome back that third of the audience who were just in New Orleans. I hope you had a good time. I certainly did. It was 25 degrees on Sunday and sunny. The snow was a bit of a shock when we got back. Good. It's a great pleasure to welcome Lucy Mason. This is her first visit to our Oxford Thursday Philosophy of Physics seminar, so I hope you will make her feel very welcome. I'm sure you shall. Lucy read physics and philosophy at Bristol with our friends there, and then moved to London to do her PhD at King's with Eleanor Knox and Alex Franklin, who again are great friends of ours. And she's currently a postdoc at Royal Holloway working with Rudiger Schack, and she's going to be talking to us about measurement, metrology, and perspectives on the quantum state. So over to you, Lucy.
Great. Thank you so much, and thank you, Chris, for inviting me. Is the online sharing all right? I'm not sure.
I think it should be. I think it'll be fine. Yeah.
Okay, great. Get started then. Yeah, so it's great to be here. I've managed to never be able to attend the seminar because I'm always teaching on Thursday afternoon, so it's nice to be here. So I'm talking about measurement, metrology, and perspectives on the quantum state. So the project I'm on as a postdoc is about this kind of topic and about how metrology interacts with quantum mechanics and how it can kind of push us to different interpretations of metrology and different work in that area, but also how metrology can help us understand quantum mechanics and the different interpretations of quantum mechanics. And so that's kind of what I'm going to be looking at today, is how this kind of a formal study of measurement can help us with interpretations of the quantum state. So I'm not doing whole-scale interpretations. I'm staying away from the measurement problem, despite this being a talk about measurement. But in general, I'm kind of assuming a background of Everettian interpretation, many worlds, taking quantum mechanics as is with no modifications. But I'm particularly interested in the quantum state and the different kind of ways to be realist about the quantum state. So the plan for what I'm going to say is start by looking at the idea of perspectives. So I'm going to draw a distinction between the first person and the third person perspective, and argue that depending on the perspective you take is what pushes us toward different interpretations that are available of the quantum state, and argue that there's this whole array of different positions on what the quantum state is, what it tells us about the world, what the ontology is. And I'm going to argue that depending on the perspective you feel yourself taking leads you to different answers for what the quantum state is. And I'm then going to basically say, looking at the first-person perspective and the interpretations that go along from that, looking at measurement, I'm going to say that perspective is the best current option for explaining measurement based on the way that measurement and properties and the quantum state are used in the metrology literature. The way that measurement relies on properties should lead us towards this style of interpreting. But I'm also going to look at how that perspective is limited, and how reconciling between the first person and the third person perspective can help us understand measurement through the first person perspective, but also situate it in a broader third person view, which gives us a lot of other benefits in other ways, and kind of say that these interpretations of the quantum state that are normally seen as two options you have to choose between can actually be reconciled, and if we approach it through perspectives, we can start looking at getting the benefits of both. Okay, so I'm going to start with this analysis of perspectives and the different interpretations. So, as I said, I'm going to look at the third-person perspective and the first-person perspective. So, the third-person perspective is fairly intuitively the style of kind of third-person literary narration. It's the world independent of us or without us in it. It's kind of often seen as the default view of science, the kind of objective view of like as if it's on a lab table and we're kind of looking down, doing our models, with no reference to us or our place in it. We can definitely model ourselves as part of it, but we don't model it from our perspective. We model ourselves as another type of physical system in the rest of the world. This is opposed to the first-person perspective, which is less familiar and more contentious in a lot of ways, although there's a lot of interpretations and styles of quantum mechanics that rely on it heavily. But the first-person perspective is about modelling the world from the position that we have in it. So situated in the world with certain means of interacting with the world around us, so acknowledging that we're a physical system with certain limitations, certain styles of measurement, certain styles of interaction, and trying to create a model of what the world looks like to us in our situated position. So the first-person perspective I'm interested in is not one that's linked to consciousness necessarily. It's not about being a subjective agent. There's obviously styles like cubism and that kind of style of quantum mechanics, which are linked to that. I'm taking a more objective physicalist kind of first-person perspective. So it's much more based on the process of measurement, so how we interact from where we are with the objective world. But the observer is just a kind of placeholder like we have in special relativity. So it's like a reference frame defined in terms of an observer or point of view. But the observer isn't an essential part of it. There's no need it has to be a human observer either. So there are kind of various approaches in the literature. So I think Emily Adlam's written recently about this sort of perspectivalism as a kind of general way to analyse perspectives. I am interested in the perspective of a person, so an observer or human observer. But again, that doesn't mean a conscious observer. So I think the kind of perspective I'm talking about is most similar to kind of causal perspectivalism. So the ideas of causal perspectivalism is that certain concepts like causation are relevant to us as agents because of the way that we're situated and have access to certain information through kind of emergent thermodynamics and that kind of idea. And that from that perspective, concepts like causation are explanatory relevant, even though they may not be fundamental. So that's very much the idea I'm going to run with the first person perspective. So we have these two perspectives. They're normally seen as, I'm calling them perspectives here. Frankly, the third person perspective is normally not called a perspective. It's just called the objective view, the view from nowhere even. I want to emphasize that it is another type of perspective which shouldn't be seen as more fundamental than the first person perspective, or at least that the first person perspective can't be eliminated in favor of this more objective third person perspective. So what I want to say is that depending on which of these two perspectives you take, you're going to be inclined towards different interpretations of quantum mechanics. So if I'm in the third person perspective, I want to model the world independent, treating everything the same. So I want to treat everything in terms of the quantum framework, including observers, including everything, which is probably going to lead me to a kind of state or wave function realist view, which interprets the world entirely using the quantum framework. It takes the quantum state as the fundamental ontology in some way. So it's fitting with the third person view of being objective, viewing everything in equal terms. In contrast, the first person perspective is going to focus me on observables, because I'm looking at how the world appears to me. So I'm going to look at the observable properties and base my interpretation on those observables. So to go into these distinctions a bit more, so obviously there's a lot of different views on more precisely how to interpret the quantum state. So obviously with state or wave function realism, there's significant differences between those two views in terms of the ontology. So wave function realism is obviously going to take the quantum state as a point in a vector in Hilbert space or a point in phase space and take that as the fundamentology. The state realism, I'm thinking of something along the lines of kind of Wallace and Timpson's space-time state region, where the state is assigned to a region of space-time. But again, the quantum state is taken as a kind of fundamental part of the ontology. And so in terms of kind of picturing this, I often think this is the way that the kind of picturing the quantum state in terms of the block sphere is going to push us towards thinking of the quantum state as a kind of unique mathematical object that we interpret in terms of that mathematics, that kind of mathematical concept first and foremost, and any observable properties are derived from it. The observable first approach, in contrast, is much more focused on the kind of historical evolution of quantum mechanics, so the kind of Copenhagen views, neo-Copenhagen interpretations, quantum logic, metaphysical indeterminacy literature uses this view a lot. And it tends to lend itself towards speaking in terms of experimental phenomena. So saying, the quantum state is in a superposition, the electron goes through both slits. That language we don't really find in wave function realism because it's kind of interpreting it in terms of a classical observable properties, and they want to emphasize that those are derived properties and we should be paying attention towards the wave-like state. But the observable first approach is really interested in pinning down those observable properties and using that as the basis from which to explore the quantum world in more depth. So that's a kind of rough characteristic. Again, there's a lot of differences between the individual views, which I'm kind of glossing over, and drawing this distinction between these two approaches. So to go into more depth, one of the main differences between these two styles of interpreting the quantum state is in terms of how we assign properties to quantum systems. So I'm trying to characterize a system. What properties does the system has? The state or wave function realist view often they're kind of maths first, structural realists who don't want to talk about properties at all. But to the extent that they do, they want to say that the wave function is the properties we care about. So properties like being in an entangled state or possessing an even number of zero amplitudes in configuration space, these very kind of mathematically driven understanding of properties which are very closely tied to the quantum formalism. And then the observable first approach, obviously properties are represented by projection operators. So a projection operator defines a particular property, and the eigenstates represent the system having particular values of that property. And they're going to be familiar properties like position, momentum, and that kind of thing, which the state or wave function realist view don't see those properties as a kind of key part of understanding the quantum state. So these different kind of properties they're talking about, the state or wave function realist wants to recover observable properties at the decoherent level, which I'll go into later. But fundamentally, they want to deal with these new type of kind of quantum properties that are quite distinct from the observable ones. So one of the key parts of the observable first view is the eigenstate-eigenvalue link. So that's what helps us make sense of quantum properties. So this is kind of one of the central points of dispute between the two approaches. So the state or wave function realists almost universally reject the eigenvalue link as a fundamental part of quantum mechanics. So the eigenstate-eigenvalue link is often used a lot when we're teaching quantum mechanics because it's simple, it's intuitive. The way that we teach the mathematics of quantum mechanics, we start by saying there are projection operators. They are defined in terms of a set of eigenstates with eigenvalues. And the eigenstate-eigenvalue link just very simply says what it means for the quantum system to have the property determinately is for it to be in an eigenstate of that projection operator. And then the property has the value, say position x, it has the eigenvalue as its value for position. So this is the central part of the observable first view. So it's everything they do is based around this premise essentially, and the idea that this is what it means to be an observable property, to be that determinately. And then they have a whole literature on what it means to have a property but not determinately. So being in a superposition is when this link fails, when you're not in an eigenstate, you're in some kind of superposition of an eigenstate. Then they have to work out a system for saying, well, it has the property, but it doesn't have it determinately. There's no single value, there's no single eigenstate, no single eigenvalue. But they do take it to be a fundamental part. The state and wave function realists see it as useful to teach quantum mechanics, useful as a kind of shorthand, but as a kind of separate addition which isn't part of the main formalism and is normally regarded as just of instrumental value, if that at all, and often they even reject that. So David Wallace has called it a false friends and says that actually it's the fact that we teach quantum mechanics in terms of the eigenstate-eigenvalue link is missing out on actual physics practice, which uses POVM measurements rather than projection operators anyway, and it kind of misses out the complexity of what goes into a measurement. The observable first view, as I've said, embraces it as a central postulate for interpreting what a quantum system is. It defines what it means to have a determinate property. So along those lines, some other differences between the two perspectives and the two styles of approach. So the state and wave function realists think that the observable first approach can't really adequately capture the full complexity of the quantum formalism. So they think that the kind of properties that the wave function has, so things like being in an entangled state as a property of the system, is just completely missed out by focusing on observables, because it's fundamentally not something that's observable. I can't observe something being in an entangled state. I can infer that it's being in an entangled state, but it's not something I can measure directly. Debatably anyway, but most people would agree. And so they think it kind of misses out. It misses out by focusing too much on the eigenstate-eigenvalue link at the expense of more complex measurement techniques. And it misses out by basically discrediting the kind of purely quantum concepts that have emerged through the development of quantum mechanics. So people like Maudlin, so I think that's name wrong there, claim that operators reduce measurement to just statistics between input and output. So an operator applied to a state, I can say if I'm using a Stern-Gerlach machine, I can say if I apply an operator to the quantum state, it gives me the output that 50% of my electrons are deflected up, 50% are deflected down. but Maudlin argues that it doesn't tell me actually what's going on in measurement, so it's just a simplification to statistics which doesn't treat measurement as a physical process, it just treats it as a input-output machine. So they're pretty anti the observable first view, but in contrast, the people who are subscribing to an observable first view don't think very highly of the quantum state realists. So they want to say that the quantum state realists overlook how important empirical data and measurement and observables were in the development of quantum mechanics. The empirical formulation was the foundation of it. Looking for links between observable results was where we derived the mathematics from in the first place. And it remains, the only testable part of quantum mechanics is those empirical foundations. And so they think that the state realist view is placing too much precedence on an abstract mathematical formalism and not directly linking it to the reality that we kind of live and breathe in and have a good grasp on. And so they want to focus on those observable properties because they think those are the ones that we actually are meaningful to us. So they're quite at each other's throats about these two differences. It means depending on which view you take, you assign very different properties to the quantum state. You take very different views of what sort of properties you're interested in, as well as the kind of central question of what your ontology is and how that relates to your interpretation. So one thing to note is that a lot of the observable first views are linked to collapse interpretations, or epistemic interpretations. I want to say that it's not a necessary connection, so interpreting in terms of observables doesn't mean that you have to subscribe to collapse or that you have to think of this as just an epistemic. It is definitely more pragmatic and more epistemically inclined version of realism, but you can still be kind of phyontic about the quantum state in this sense. So I'm kind of separating out there and saying, well, broadly, if we assume a background of Everettianism without going into the details too much, we can still look at this distinction between the interpretations. Okay, so that's a kind of overview of the different perspectives. Hopefully it's getting the gist of how the different perspectives lead us to these different interpretations, different styles of approaches. Obviously, we'll be coming back to these perspectives and hopefully defining them in a little bit more detail, especially the first-person perspective. But at the moment, I feel like this literature goes back and forth between these two approaches, and neither side are really making progress with understanding the virtues of each approach and looking at how we could come up with some kind of compromise which allows us to look at the benefits of focusing on observables and that kind of formalism, but also being able to treat physical measurement systems as just another type of quantum system in a kind of third-person view. And we don't want to give undue precedence to our position in the world. It is a very valuable project to say, well, we're not special in some way, science doesn't depend on us, so we should be able to treat ourselves as just another kind of cog in a machine. And the observable first view doesn't seem to be able to do that. There's a lot of complaints that it presupposes elements of classical theory, it presupposes observers, presupposes classical properties. So it has its drawbacks as well as its benefits. But I want to focus now on measurement and the idea that the first-person perspective and the observable first view that comes with it is better able to account for measurement. It's what the view is designed for. The view comes from thinking about measurement properties. And I want to say that the third-person view doesn't really have a strong account in comparison, based on the way that we actually think about measurements in the metrology literature. So moving on to this one now. So the first kind of premise of measurement is, looking at, Bohr obviously wrote a lot on measurement, so he has this idea that we recognise that a measurement can mean nothing else than the unambiguous comparison of some property of the object under investigation with a corresponding property of another system, serving as a measuring instrument, and for which this property is directly determinable according to its definition in every language or in the terminology of classical physics. What he means by the terminology of classical physics in everyday language is notoriously vague. He never really pins that down. But it does give a good indication of the way that measurement is thought about. It comes down to this question of properties. Doing a measurement means we take a device, a measuring device with a property such as position, which we can directly experience. We couple it to a quantum system so that the property that we can directly have access to is coupled to the property we're interested in. And by that coupling, we derive a kind of measurement results. So that obviously places a lot of weight on the property framework, which something like the state realist view, which is much more focused on mathematical formalism and its account of property, is immediately going to struggle with, because this is not described in terms of properties. The state realist view is not described in terms of properties in the way that measurement relies on. So obviously Bohr is older material now. The metrology field has moved on, but we're still seeing this in the kind of the way that measurement is talked about in metrology now. So Mary, Wilson and Moore have this book-length treatment of the philosophy behind metrology in all the different fields, in social sciences, in physics and chemistry. And they again come back again and again to measurement relying on the properties of an object. So they say an empirical property of an object, more specifically an empirical quantity of an object, such as the rod or reading comprehension ability in social sciences, is associated with the mode of empirical interaction of the object with its environment. So basically saying the same thing that Bohr was, that a measurement is about taking the system you're interested in and coupling one of its properties to the environment, i.e. your measuring device, in a way that allows you to translate that property into something observable to you. So there are sort of two things in this that I want to highlight. The first is that there is this overlooked assumption in a lot of the metrology literature where they just say, oh, it's about coupling properties to the environment. There is a specific coupling we're interested in, which is coupling to us as observers, whether that's not us as conscious observers, but us in terms of it needs to be a property that's directly observable to us. I can't just couple two quantum systems and call that a measurement. I need to, at some point, couple it to a system that's part of my environment and part of the kind of environment that I'm in. So to amplify that result up to an observable property. So that's, I think, often overlooked when we're talking about the measurement of these, of kind of subatomic physics in that kind of sense, in a way that a lot of the metrology literature is focused on classical physics or on social sciences, where those issues are not as pronounced. But we are always looking in measurement at relating the property of an object to us in our position as observers. That's what it means to make an observation. You cannot separate that from being an observer who's situated in the world. So there's an immediate connection to the first-person perspective in measurement just through that. To be an observer and to make observations requires you to be situated in the world and to interact with it. And generally, the limitations that we have on the type of interactions we can make with the world are not a big barrier. In the classical world, we're dealing with classical systems, we're classical systems. It's all the same kind of thing. We don't need to think about our particular position. In quantum mechanics, that is not true. The fact that we're classical systems and we're trying to make our observers from this position in the classical world means that there are immediate limits on the type of observations that we can make. We can't interact with the microscopic world as a microscopic system because we are classical and we exist in that world. So that's one aspect to think about, in that there's this immediate connection to the first-person perspective. But there's also a kind of slightly deeper connection, which is focusing on the requirement that measurement is about quantifying a property. We're not just kind of coupling one property of the system to a property of the measuring device, and that's it. The output of measurement is almost always a numerical value. We're looking at quantifying the property and putting a value on it, which allows us to make comparisons between systems. It allows us to kind of compare them directly to each over time or to other systems. And this has been the kind of focus of most of the literature in metrology, is about how do we go from empirical objects and kind of sense data to applying a metric scale and getting a number out. So obviously the simple example is just saying, well, if I want to make a measurement of length, I start by saying, you know, my hand is shorter than this lectern. But that's an entirely qualitative, empirical sense data observation. To turn that into a kind of formal comparison, I need to set limits on the objects I'm talking about. I need to work out and how to actually put numbers on that. And there's a lot of questions about, well, I can start doing that by saying I can compare the length of my hand on its own to the length of this plus my hand and say, well, that's definitely longer than this on its own, which means that you can map out the properties and start mapping it onto a numerical scale. So almost all measurement maps onto the scale of real numbers. very intuitively. Most things exist in a kind of physical continuum characterized by the set of real numbers. And so we often overlook the stage of measurement, which is this mapping between empirical comparisons, qualitative comparisons, and we immediately switch to saying, well, I can put that in terms of real numbers without even thinking about it. But there actually has to be quite a lot of work that goes into showing that this is a valid mapping to make. And some mappings are not simple at all. So temperature is notoriously difficult to do this for because there's no simple additive relation in temperature. I can't add 2 temperatures and get double the temperature. Like numerically, obviously we can, but in terms of experiencing temperature, the phenomena of temperature that it's latching onto in the world, there's no clear answer to what it means to double the temperature. There's a different type of scale than, say, length scale is. And so there's been a lot of work done to work out things like, well, what scale does temperature correspond to? What mathematical properties does that scale have? And how does that allow us to actually quantify a value for temperature? And that's not even getting into the issues of, where do I set my 0 points? How do I set intervals in a way that's useful? And the different possible temperature scales, for example. But all of these come back to applying a metric scale to an otherwise empirical sense data and translating that into a number. And so that getting a number at the end is the basis of pretty much all measurement. There are definitely qualitative measurements, but they're often seen as less rigorous or as derived from empirical results, which are numerical results. So if I want to say get a measurement result of an interference pattern isn't a numerical result, but I'm going to derive it from numerical results. So it's always going to come back to some element of I measure, I get a number, and then maybe I derive other results from it. But that kind of application of the metric scale is behind all of that, even a lot of qualitative results, and it's going to be used at some stage in every measurement. And a lot of our measurement results are just straightforwardly, I measure position of a quantum system. I want to know where it is. I want to know which path in an interferometer it went down. That kind of directly measurable numerical result. So I want to go back now to the eigenstate-eigenvalue link, because the eigenstate-eigenvalue link, its strength is that it's directly meant to capture this recognition of applying a metric scale in measurement. So the idea of having a determinate property, of saying there is a property, it has this value, is the foundation of interpreting a result like the position is x plus or minus some uncertainty in the position. What I'm doing when I state a result like that is I'm saying this system has a property, position, and it has a value of that property. It's x. I have some uncertainty in that value, whether that's due to fundamental quantum fuzziness or whether it's due to measurement error. Those kind of uncertainties are kind of run together just to produce this one numerical output. And we associate that with the idea that the quantum state has a determinate property with a determinate value. And that's what the eigenstate-eigenvalue link captures. What it means to have an eigenstate is what it means to have a determinate property within the quantum formalism. That's very simple in classical mechanics. We don't need a special link because all properties are determinate, so we don't have to spell it out. Quantum mechanics introduces the possibility that our results aren't determinate and that the state may not have a determinate property, value of a property. So we have to spell out this rule more explicitly than we normally would in measurement. But that's kind of what the eigenstate-eigenvalue link is designed for. And even in cases where the eigenstate-eigenvalue link doesn't strictly apply, so if I'm using a POVM measurement, it doesn't collapse the state to an eigenstate, it's a kind of approximately localized state instead, but we still use the eigenstate-eigenvalue link as a kind of guiding principle to interpret the result. If I do a POVM measurement in the lab, I still get an output x plus or minus uncertainty, and I interpret that as that means it's pretty much in position x. And so even when I'm saying I'm explicitly recognizing that it's not in an eigenstate, the way I'm reporting the results of a measurement are still reliant on that sense of this is what it means to have a determinate property. So the fact that we don't use it literally, I think, is a way of masking how central it is to the understanding of quantum mechanics. Because even though it's not an essential part of the mathematics, it is an essential part of understanding empirical results. So that obviously makes the first-person observable first view fit perfectly with the way that properties are thought of. It's what the first-person observable first approach is designed to do. It's designed in terms of observable properties, which are the ones that we apply the eigenvalue link to and interpret in this way. So they're directly, easily quantifiable properties which fit in with the understanding of measurement we have across all of the sciences. In contrast, the third-person account of measurements along the lines of a state or wave function realist, they haven't really spelt out in much detail what they actually think about when it comes to measurement. So there's a kind of hand-wavy explanation of this. Oh, well, observable properties are recovered through decoherence. Job done. That's fine. We've got everything we need from observables just through decoherence. So obviously the process of decoherence is supposed to transform the state by interaction with the environment, and it will single out certain properties in a certain basis. It will make them adequately stable, approximately diagonalize the density matrix in a way that gives me robust predictions, the robust predictions of classical mechanics. So I get roughly the observable properties that are captured by operators back in that way. And other than that, there's no real discussion in the wave function realism literature about measurement specifically, despite measurement being a kind of central part of quantum mechanics. It's just assumed that this covers that situation, the decoherence covers it, and there's no further details to be spelled out. But ultimately, the way the wave function realists are talking about properties is very, very different from the way that observable properties are spelled out. So observable properties have this intuitive understanding of they are the ones we understand to be quantifiable. They're like observable properties of position, momentum, which we have done huge amounts of work over decades of metrology literature in applying these metric scales to working out exactly what the additive properties and what numerical scales are suitable for these properties, and how the measuring devices are kind of capturing that scale, how we transfer between sense data and a numerical output. And the wave function realist properties, things like being in an entangled state, properties of even number of zeros in a configuration space, those kind of mathematical properties are not ones that we've really done that for. We don't really have a good grasp on how those relate to a metric scale, how those relate to quantifying something in the lab and switching between sense data and metric scale. And so it's all relying on this decoherence link to just get us back the properties we need and we do understand in the context of measurement. But I'm not going to kind of attempt a full analysis of the decoherence framework here. I'm going to talk about decoherence later on anyway. But I think there's kind of two reasons to doubt whether or not the decoherence account of measurement is going to be adequate for the state and wave function realists. So first of all, there's a problem that measurement is not aimed at the decoherent regime. When we measure, we are trying to measure the quantum regime prior to decoherence. So there's the assumption that at some stage in the measurement there will be decoherence because it's necessary to produce an observable result that we can have in the lab. So there will be decoherence at some stage, but we're trying to measure the quantum properties of an object. We're trying to go beyond decoherence and look at the properties of quantum systems while it is coherent, while it is isolated in that way. And so the way we design and talk about measurement procedures is all done in terms of observable properties before decoherence takes place. So if I'm looking at an interferometer, I'm talking about which path information, so basic observable property of position, which of the two arms of the interferometer has it gone down, even when decoherence is assumed not to have taken place. And crucially hasn't taken place to get the interference result we're interested in. But I still want to be able to analyse that situation in terms of observable properties when decoherence doesn't apply. And decoherence is kind of given as a catch-all of, well, we get back observable properties, which overlooks the fact that it is a dynamical transformation of the state. It's not a kind of static process. It's not something we can just apply on and take off. It transforms the state you're interested in. It changes the dynamics of that state. It changes the behaviour. So saying that decoherence just covers the whole measurement situation when it's a process that takes part at a very specific stage of that measurement seems to be overgeneralizing the role that decoherence is playing in that measurement. And the fact that we still want to talk about observable properties in the parts of the measurement not affected by decoherence means that I think we need a better explanation for where observable properties are featuring in the measurement. There's also the fact that the decoherence program focuses on the emergence of classical dynamics, but we do not treat the results of quantum measurements as classical. We do not say, well, we get out a classical result and all our results are classical. We want to say, when I measure the position of a quantum system, it's of a quantum system. It's not of the quantum system when it's effectively classical. So again, we're looking at this system when it's still in a coherent stage prior to decoherence, but I'm applying observable properties even then prior to decoherence. So if we want to say the decoherence account isn't enough, then there are alternatives to that approach. So David Glick has suggested seeing observable properties, the kind of quantifiable properties, as functional roles that the system fills to a greater or lesser degree. So saying that, well, when I say a system has a position, I'm saying that the quantum system fulfills the role of being a system with a position to some degree, but it's not a perfect match. That language is something that I've applied because talking about positions is useful to me. And the quantum system isn't defined in terms of things like position. I just kind of make a map between the quantum system as it is and kind of concepts I'm interested in, like position. So he compares it to explain a functional role, he compares it to talking about a doorstop. So if I analyse whether or not an object is acting as a doorstop, I'm not really telling you anything about that object. I'm telling you how well it fulfills the role of stop, which is something that I have interest in. I want the door to stay open and I'm using this object for it, but the object is not fundamentally a doorstop. Its actual properties are things like weight and mass and coefficients of friction and all of those kind of things which determine how well it functions in that role. But that property that I'm interested in of being a doorstep is something that's just for me. So he doesn't spell out that kind of analysis of measurement in much detail. I think there are some immediate problems of it in terms of how unintuitive it is to the way we think about quantum measurements. To say that all of these measurements are just a measure of fit between the object and an entirely operationally defined role, there's something kind of unintuitive about that, which hasn't really been explored. It also makes it a bit mysterious what the actual numerical result means. Because if I report a result, I measure position, it's x plus or minus uncertainty, I'm no longer saying, well, there is a property of the system x and it has this value x. I'm saying, well, there's some measure of fit between the object and my functional role, which is somehow captured by this numerical value, but in what sense it's capturing that measure of fit is not really clear. So outside of quantum mechanics specifically, there are more general operational accounts of measurement which define properties in this kind of operational way by saying, well, there's this set of operations we use to determine a property, and then we use those on various systems to get a value and to see how much that maps onto the empirical results we're after. So I'm not going to go, there is a lot of literature on that. I think there are known problems with those accounts, which come with how it deals with measurement uncertainty, transferability across measurement context, because it puts all the focus on the measuring apparatus and saying, like, the set of procedures I go through when I'm measuring something in some way determine the property that I'm interested in. Because I can no longer say, well, it's a property of the system. Instead, it's a property that I've defined using my measuring apparatus. If I slightly change my measuring apparatus, do I have a different property? How do I even talk about uncertainty in that sense when the uncertainty is, almost built into my measuring apparatus rather than into the object? So it no longer becomes a kind of epistemic uncertainty, it becomes an uncertainty in the definition of my property. So there are known problems, there are better accounts, worse accounts of that, but most of them haven't been explicitly applied to the state realist view in the particular way that it thinks about properties and the particular way that it talks about, the mathematical structure and how this relates to observable properties. So if these accounts are going to be viable, I think they need a lot more work to make them viable and to actually explore what it really means, what they're really saying about measurement and properties in measurement. So summing up all of that, the first person observable first view, it's quite a mouthful, sorry, I was saying all of that at once. But that view is readily compatible by design with the properties used in metrology. It's based on well-established properties or we understand how we can apply metric scales to, we understand how to use them in measurements, job done. And it also is intuitively linked to measurement in the sense that measurement is a first-person activity. I am measuring the world from my position. So it seems ideally suited to explain measurement. And it allows us to characterize quantum systems as objects of empirical investigation. So if I define a quantum system in the observable first view, I define it in terms of its properties that are functionally relevant to me. I define it in terms of the properties that I can see and observe and interact with and get measurement results for. So it allows us to readily talk about experimental situations and the empirical data we get to support quantum mechanics. Comparatively, the third-person state or wave function realist views don't have a well-developed account of measurement. They rely on decoherence to solve all of their problems without an in-depth analysis of how that would actually work. I've given some light reasons to doubt that it is enough. It's not a full-blown takedown of it's absolutely impossible for them to do that, but at least indicative, I think it's a bigger problem for them than they think it is, and that if they do want to maintain that they can explain measurement, they need to do a lot more work to develop exactly how that works. So that's the reason I think that the first-person perspective is better able to give an account of measurement than the third-person perspective. So for the last 15, 20 minutes or so, I'm going to focus on how the two perspectives can be reconciled. Because there are obvious drawbacks of the observable first perspective. The main one is that it assumes that we have well understood classical properties without explaining how those come out of a fundamental ontology. So it's reliant on the classical realm. This is the biggest objections to things like the Copenhagen interpretation, which relies on this observable first view, is that it presupposes classicality in a way that seems problematic, and it seems like we're prioritizing the level we're at with no basis and no interest in the fundamental ontology. So looking at how they can be reconciled allows us to maintain the value the first-person perspective has in explaining measurement, but fits it into a broader picture which we can use to look at these broader questions of where classical concepts come from, how we are just another type of quantum system, ultimately, and answering those kind of questions. So I'm going to go through how decoherence can be used in a different way than what the way I've just described, and can be used instead to justify the first-person perspective. So the standard story of decoherence is that classicality emerges through decoherence. So I interact the system with its environment. This is the process that picks out those observable properties, but it also allows me to derive classical dynamics, classical properties, classical information theories. That's the kind of standard picture of decoherence. But I think an overlooked aspect of it, especially in the historical development of decoherence theory, is that it also derives observers out of an otherwise quantum world with just systems. It creates the world in which observers operate, and it creates the conditions which they rely on, and allows us to kind of define the first-person perspective existing at a kind of classical level, like we exist in every day, but coming out of quantum mechanics. So starting with a kind of historical look at decoherence, so the decoherence picture started with the consistent histories framework, which then turned into the decoherent histories framework. So coming from Gell-Mann and Hartle in particular, the decoherent histories, they obviously have the whole framework. I'm not going to go through the technical details of decoherence, but I think one aspect that's been overlooked in their program is that along with deriving classical dynamics and sets of classical histories, they really focused on the role of observers. And they thought at the time, in the kind of 80s and 90s, that part of the decoherent histories program was that once you had a set of coarse-grained histories which gave you classical dynamics within each history, to choose between the histories, you would then have to add in a theory of experience of some sort. And they never really pinned down what the theory was, but the idea was that, well, there is going to be a point where in your theory you have decoherence, but to make the final part of it work and to say, well, why do I have this history and not that history, that would be an answer of the role of the observer in quantum mechanics. So it started off as an extension of the Copenhagen interpretation in that sense. So the most concrete work they did on this was to add IGUSes as model observers, so an information gathering and utilizing system. So the sort of system we are. We take in perceptual input, we process it in some way through memory and stuff like that, and then we use it to predict and act in the world. And they added these models of observers into their framework to try and work out how they could be used to solve something akin to the measurement problem and choose between various sets of histories. I don't think it really got anywhere. It hasn't been taken up particularly, but it was it's an illustration of how important observers were to the evolution of the decoherence program and how they were taken to fit the overall picture that created. A more recent development that's picked up on that is quantum Darwinism. So quantum Darwinism is an extension of decoherence theory from Zurich, which looks at, rather than looking at the diagonalization of the density matrix, which is what the standard decoherence picture does, it instead looks at the environment and the information that's transferred from the system into the environment, and looks at saying, well, there's lots of records created in the environment, and that's how measurement works. So the kind of formal result it derives is classical information theory and various bounds on sorts of information. It also claims to derive intersubjectivity. That's debatable, especially in terms of the kind of Leibniz-Friend paradoxes and those kind of questions about intersubjectivity. But that's the aim anyway. Zurich says he's derived intersubjectivity. And again, this is very much looking at modelling the observer and saying, well, how do I get an observer as the endpoint of a measurement which involves decoherence? So sometimes this is taken very literally in the sense of it literally models an observer. Sometimes it's taken more widely. So it kind of has this evolutionary picture about how decoherence, and quantum Darwinism in particular, defines the kind of classical conditions which observers rely on, but doesn't model them directly. But the aim is to model observers in the way that observers are the endpoint of measurement in decoherence. The extent to which it is successful is still debatable. I think there is a lot more work to be done. But that's definitely where the decoherence program is aimed at in a lot of ways, of saying, well, we create this emergence of classical world, and then we add in observers as the endpoint of that process. So that's a kind of brief tour of decoherence framework. But that also is looking at observers in a kind of third-person way. So these are these stories about how I start in a third-person framework, looking at the quantum state, so I can be a quantum state realist at this point, apply decoherence, and I get a world in which I can add in my little model of the observer and see what they do in the world. So what does this mean for the observer themselves and how they view the world from that position? So observers are put in at the endpoint of decoherence. We rely on living in a decohered world. We rely on classical concepts, the kind of stability that classical concepts have. So, the fact that position is stable is the kind of foundation of our experience of the world. Things have stable positions. We rely on that. And all our interactions with the quantum world and looking at quantum phenomena are filtered through decoherence. We exist in this position as observers because the decoherence has created a world in which the kind of observers we are can exist. So that is ultimately going to colour the way that we interact with the world. Because everything's filtered through decoherence and we rely on classical concepts to operate as observers, this is going to mean that when we're saying how the world looks from our position, we're going to rely on those concepts to explicate that. So going back to Bohr again, so I used him as the example in the measurement literature. He's also been very influential in the decoherence literature. So he has this whole thing about classical concepts. So he thinks that however far phenomena transcend the scope of classicality, the account of evidence, so empirical results, must be expressed in classical terms. Because by experiment, we refer to a situation where we can tell others what we've done, what we've learned, and share results. So intersubjectivity is a big part of this. And to do this, the account of experimental apparatus must be expressed in unambiguous language with suitable application of the terminology of classical physics. That phrase repeated, again, it was in the earlier quote, if you can remember that. And again, it is very vague what he means by this, but it has been very influential in the decoherence program, was trying to fulfill this aim of saying, well, how do we get the classical concepts that we rely on, that Bohr's kind of saying is essential to measurement? So one way of interpreting what he says is that, To explain measurement, we have to distinguish between us and the system we're measuring. That's ultimately already a classical assumption because we're ignoring entanglement between us and the system. We're saying I can be well defined, that system can be well defined, and then we can have a easy interaction between the two systems. So elements of classicality are creeping in just by doing that. And he kind of goes further and kind of saying, well, that goes into how we define the measuring apparatus by laying out this is a measuring apparatus and this is the system that we're interested in. Again, we're making a separation that doesn't exist within quantum mechanics on its own. So the decoherence program in general has tried to take this up by explaining how we can derive that split between system and environment from within quantum mechanics and how we can use that to get that for free rather than having to presuppose it as the Copenhagen interpretation that was inspired by Bohr had to. They had to presuppose the classical concepts. Decoherence wants to derive them. Again, the success of the decoherence program is not absolute, but I'm going to put aside kind of questions about how successful it's been and just say, look at it and what it aims to do. And it aims to explain why we switch into classical modes of description when we do measurement. That doesn't mean it perfectly delivers what Bohr was aiming for, but Bohr was part of the inspiration of it. So Zurich's work in quantum Darwinism talks about this very explicitly. He thinks he's delivered the kind of amplification to the classical level that Bohr was talking about. In terms of decoherence histories, so this kind of historical review of decoherent histories says that the purpose of decoherent histories was to derive the quasi-classical world that provides a home for Copenhagen interpretations. So it provides a home for the assumptions that the Copenhagenists were making, which was to assume that we need classical concepts to explain measurement. So nearly at the point of wrapping up, and to kind of start summarizing what I've gone through, being in a first-person perspective means that we have to understand the world through the mechanisms we have available to us. And those mechanisms are measurement, and they are decoherence. We have to look at things filtered through decoherence, because decoherence produces the kind of classical world that we rely on and that we can have direct sense data of. So we're limited in the terms of the picture we can have of the world because of our reliance on these concepts. So this requires to adequately explain how the world looks to us through measurement. We have to take the observable first view of the quantum state, which uses these concepts that we rely on to characterize the world. So it represents it as a superposition of classically understood properties, which are discoverable through measurement. That's how the world looks to us, and it's important for us to use that to explain measurement results. And we don't just use this in measurement scenarios, we generalize it beyond that because we want to talk about potential measurements and what is measurable, what isn't measurable, not just what has been measured and has been affected by decoherence already. But at the same time, as good as the observable first approach is for explaining measurement, we still want to situate it within kind of broader third-person state realist view, which allows us to look at where the concepts we're relying on come from without presupposing them. So looking at this in terms of perspectives allows us to separate out the question of how do I rely on classical concepts when I'm doing measurement from the question of where do those classical concepts come from, why am I justifying using them, and separating that out into kind of two distinct projects and two distinct perspectives, which ultimately we can reconcile by looking at the emergence of observers, but can be treated differently when we're looking at these separate questions. Okay, so to sum up the kind of overall argument I'm laying out, various different stages. So I started with this analysis of perspectives, so saying that taking a first-person perspective leads us to an observable first view, where we're interested in interpreting the world as it looks to us in the situated perspective that we occupy. If you're taking a third-person view, where I'm kind of abstracting myself from the picture and looking at it as a kind of tabletop view of the world, then the natural result of that is to take a state or wave function realist view, which works entirely in the quantum framework. It treats all the systems as the same and on a par without giving any special role to the observer. Based on these two views, they seem to be incompatible, but I've said that the first-person perspective is actually better suited for providing an account of measurement. It fits in with the metrology literature, the reliance on quantifiable properties and the application of a metric scale. in a way that the third person realist view struggles to match and hasn't really done a lot of work to spell out in much detail. And the third person perspective does not have a well-developed account of measurement. Its reliance on decoherence kind of masks the broader issue, which is the way it treats properties, and it kind of says, oh, we can get them back at the level of properties. And I kind of suggested that that's not really an adequate explanation of measurement. The option is still open for them to work on that and explore. I haven't said it's absolutely impossible for them to do it, but I will lay that as a challenge for them to do. But I've also said that looking at how the first person perspective is established through decoherence can reconcile these two views, and we can have all the benefits of the first person view while situating it within a broader third person account of the world, which removes the need to have a third person account of measurement and makes use of the first person's perspectives natural fit for explaining measurement, but situates it and allows us to analyse what preconditions go into that perspective, how we rely on it, where it comes from, and separate out those from questions of measurement. And that is it.